B-29. Pretty big. The B-36 was the most American thing that has ever happened. I'm convinced of it. 16 guns, 80,000 pounds of bombs, the biggest bomb ever made by the US, another plane inside it, and a nuke on that plane, 6 piston engines, each of which was essentially 4 engines mashed together and mounted on backwards, 4 jet engines, and maybe, if you're really well behaved, we can talk about the flying nuclear reactor variant. As always, I'll be using a mixture of digital models, real-world parts, and some physical models to explain everything. I really pushed my 5-year-old $200 3D printer to its limits this time. This took 2 weeks to print. It doesn't look as fancy as a nice kit model, but, well, maybe one of those will be appearing too later. Now, I understand that intro won't really be very interesting to my American viewers. That was just a typical day in America. But it may have had a few small inaccuracies. I just want to put them on screen right here at the start of the video so I don't spread misinformation. But we'll go into them in a little more detail later, as and when necessary. I've thought about doing a video on the B-36 since I started making videos, but where to start? It's either a crime against all engineering sensibility, or it's the best aircraft ever made. Now that I've done my research, I am swaying towards the best aircraft ever made side of that spectrum. And before we get into all the details, I do want to stress that the B-36 was an incredible feat of engineering. Flying an aircraft of that size and with a 10,000-mile range back in the 1940s was nothing short of astonishing. So, although we'll have a lot of laughs at the big funny plane, it's important to acknowledge the engineering genius behind it. It was originally conceived for transatlantic bombing runs in the event the US entered World War II after a hypothetical British defeat. It would have been very useful in the Pacific theatre, but it first flew a year after the war ended. Though initially designed for conventional bombing, it was repurposed as the US's main nuclear deterrent. A number of variants existed, and they're on screen now. I don't want to get too bogged down in all the variants, but no, some had defensive turrets, some didn't. I'll discuss variant specifics as and when relevant going forward. About 6 months ago, I did a rather in-depth video on the armament system of the B-36's predecessor, the B-29. The B-29 turret system can only be described as a masterpiece. The absolute pinnacle of 1940s mechanical and electrical engineering. So it's only logical I do a video on the B-36 turret system. The problem is, it wasn't really very good. And we'll be discussing why in depth today. I'll reference my prior video throughout this one, but you don't need to watch that to understand what I'm talking about. But the B-36 armament wasn't just turrets. So I decided to do a video on all of it. The targeting radar, the Parasite fighters, the multiple and varied bomb loads, and even a few things that weren't even built. The turret system may have been questionable, but the aircraft itself was still wildly impressive. It could even be said that the main defensive capability of the B-36 was its service ceiling, so we'll discuss those engines too. I suppose I need to say the thing, since it's basically guaranteed to be the top comment. 6 turning, 4 burning. Quick recap on the B-29 turret system. There were 4 rotating turrets and 1 tail turret. All guns were 50 caliber with the exception of a 20mm autocannon on the tail in some variants. The system was manned by 5 crew members. Each was provided with a sighting station which could rotate in azimuth and elevation, and that station was electrically connected to a turret. Point the station at a target and the guns would point in that direction too. Except there was a computer between the sighting station and the turrets, an analog mechanical computer. That not only took inputs from the sighting station, but from a panel which passed on altitude, wind speed and temperature. The computer outputted corrections for lead, wind, gravity drop and parallax and altered the alignment of the guns accordingly. Not so they were pointed at the target, but so they were pointed in the correct direction for the bullets to hit the target. And it didn't stop there. Those computers and sighting stations were networked together. Gunners could take control of multiple turrets at once. A gunner could pass control of his turret to another gunner as a target moved out of sight. And a disabled turret didn't leave a crew member with no firepower. Contrary-wise, a disabled crew member didn't leave a disabled turret. The B-36 fire control system had more guns and they were bigger, and that's about where its advantages over the B-29 system end. Some of them did this too, though it's extremely questionable whether that was actually an advantage. 16 20mm autocannons. And yes, I think that is the only time we'll be using non-freedom units in this video. The guns came in pairs, giving a total of 8 turrets, and 8 turrets needed 8 crew members. This was less sending freedom seeds down range, and more like 8 guys spraying freedom seeds all over the place, creating an extremely sticky situation for any MiG-15 who wanted to get involved. Those 8 gunners were stationed here. Each of the 6 rotating turrets had a dedicated crew member. Kind of. The nose turret was manned by the navigator, and the right forward dorsal turret was manned by the co-pilot. The latter does seem like an afterthought to me. I'm not really sure having the co-pilot of a 10-engine super bomber get out of his seat and start shooting at enemy aircraft is exactly what I'd describe as optimal. The tail gunner sat at a station in the rear crew compartment. Much like the B-29, the B-36 contained 2 pressurized crew compartments connected by a tunnel. A little trolley was needed to transfer through the tunnel given the length of the aircraft. While we're on the topic of crew, here are the other stations for a basic crew. In addition to those mentioned, there was of course the pilot, the bombardier, flight engineer, radio operator, and radar operator. Though the B-36 was huge, many accounts paint a pretty miserable picture of the crew conditions. The bunks were often removed or occupied by equipment, so were not usable on the up to 40-hour flights. And the canopy of the forward section would usually form condensation which dripped on the crew throughout the flight. Unsurprisingly, recruiting gunners was an ongoing issue. With the end of World War II, many experienced personnel had left the military, and Strategic Air Command even tried alluring Air Force chefs and military police into gunnery jobs. The result was not only a lack of well-trained and experienced gunners, but a shortage of experienced ground maintenance crew. As we shall see, this heavily contributed to ongoing issues with the armament system that were never fully resolved. As with the B-29, the B-36 fire control system was manufactured by General Electric. The front and rear turrets will be discussed separately, but each of the dorsal and ventral turret stations was identical or a minimally upgraded version of the stations used on the B-29. Like the B-29, they were connected to the turrets via a targeting computer. Those computers again were almost identical to those on the B-29, but were somewhat simplified, as we'll see. I'm not going to go into detail on how those computers worked, as I spent 45 minutes doing that in my B-29 video. The computers used an identical station to that in the B-29 to receive the wind, altitude and temperature data, but the computers on the B-36 were not networked. There are a few reasons for this, and all of them have the same root cause, that really long fuselage. With a full load of ammunition, the entire armament system weighed about... Actually, pause the video if you want, take a guess. It weighed about 14,000 pounds. That is an awful lot. With the fuselage being so long, it was decided that the wiring and additional electronics necessary to network the computers would eat unacceptably into the bomb load or the range. That long cantilever on the front flexed sufficiently during flight and caused enough misalignment between the front and rear stations and turrets that the sighting system would be thrown off, rendering it ineffective. And the greater distance between the fore and aft stations compared to a B-29 would require a greater parallax calculation. The computers in the B-36 only had to make a single and smaller correction between the relatively close-in gunner and turret. So the B-36 computers were a little simpler than the dual parallax computers used on the B-29. I think an important point of note is that the B-36 turret system was conceptualized and refined largely over the course of World War II. It was originally to consist of crewed turrets, but switched to remote turrets during its design. These turrets and their associated computers were designed to direct fire at relatively slow-moving propeller aircraft. Shortly after the B-36 entered service, the Soviets began fielding the MiG-15. The absolutely abysmal performance of the B-29's superior fire control system against these fast jets during the Korean War probably tells us everything we need to know. Though, now I've become aware of the crew recruiting issues during the Korean War, who knows? Maybe the B-29 turrets would have performed better against MiG-15s had they flown with better trained gunners. I doubt that's the case, since those analog computers were specifically designed for use against piston aircraft, but it may well have been a factor. All that said, it does appear quite likely the B-36 was essentially immune to Soviet interceptors for the first few years of its operational life. We can talk about that later in the Propulsion chapter. Let's go through the turret system in detail, and I'll go through all the major known issues at the end. The real party trick with the B-36 dorsal and ventral turrets was the fact that they folded away into the fuselage. At first glance, these appear as one of those post-World War II US blank check initiatives, but they were actually essential for the aircraft to achieve its design goal of a 10,000-mile bombing radius, preferably with 10,000 pounds of bombs. Chuck Hansen, in the book A Comprehensive History of America's Big Stick, a book, by the way, which will be referenced several times in this video, recalls that an increase in the aircraft's drag coefficient of just 0.001 would require an additional 2,100 pounds of fuel to maintain that range. Although the B-36 was huge, it was at the cutting edge of aerodynamic design for the time, and maintaining that range took priority. So, let's take a look at the folding mechanism. It was actually reasonably simple. Here's a photo of a physical model of it made by General Electric. Apparently this model was 19 inches in diameter, and by the way, it's the reason I decided to 3D print an entire B-36. We see how the turrets folded inward and were covered with sliding doors normally. The turrets sat on a ring which allowed them to rotate in azimuth, and that ring sat in a saddle mounted to a movable arm which contained a knee joint. To deploy the turrets, a motor here would actuate the arm whilst tensioning a cable to actuate and lock the knee joint in place. The added complexity of this mechanism limited each turret to 100 degrees in azimuth either side of the aircraft broadside. As for the detailed design of the turrets themselves, I honestly don't have a huge amount more to say about them from a mechanical perspective. I have a copy of the parts manual, so I'll show some images on screen throughout the rest of the chapter. I don't like adding text overlays to images, and I know it's difficult to listen to me speak whilst reading them, but feel free to pause for more info. If I narrated every detail, these videos would last for hours. By the way, I know I always make jokes about freedom units, and yeah, they're just jokes, but this one is serious, right? Americans, why is paper a weird size over there? It doesn't scan cleanly in my scanner. I'm probably just going to leave the blank space around the scans and not crop it out to make some kind of a point. You can make arguments against not using SI units, fine, but I cannot come up with a single argument against ISO 216 paper sizing, except for we've always done it this way. Right, anyway, exactly as with the B-29, the turrets were controlled via Selson motors. You can see me demonstrating a mock Selson motor here. In short, one half of it lived in the gun sight, the other half lived in the turret. The turret half mirrors the rotation of the sight half, except, of course, there was the computer in between the two providing corrections, so the Selson rotor on the turret didn't match the input exactly. The output current of the Selson was amplified significantly and used to drive the DC azimuth and elevation motors on the turret itself, and the large DC current was provided via thyrotrons. I'll discuss Thyratrons in a little more detail later. A difference between these turrets and those on the B-29 was the higher mass. More mass meant more current and bigger drive motors. As always, this would have consequences. The guns themselves were twin M24A1 autocannons, later upgraded to M24E2s. During the design phase of the B-36, the intention was to do what the Americans did to basically every aircraft during World War II and fit it with 50 caliber guns. However, later in the design, it was decided to increase defensive firepower and switch to 20mm guns. This is mainly the reason for the high mass of the overall turret system, and it significantly complicated development as new hardware had to be developed to accommodate the new guns. Again, this would have consequences. The real kick in the teeth came during the gunnery trials. It turned out that in the rarefied air 40,000 feet above sea level, 50 caliber bullets actually had better ballistic properties than the larger and heavier 20mm rounds. This wasn't known during World War II, as there were no aircraft that could get up to that altitude to test out the properties of the guns. Tests on the ground showed that 50 caliber guns would have been perfectly effective against MiG-15s. The 20mm guns caused nothing but problems. The 50 caliber Browning that they replaced is still in service today. The B-36 tail turret system was distinct from the other turrets. Rather than using the visual sighting stations, it was radar controlled and operated by a dedicated gunner in the aft section of the aircraft. As we shall see, the tail turret was by far the most important of the entire system, so use of radar to improve accuracy had already been established on the B-29. Towards the end of World War II, radar-controlled turrets were trialled in combat, but performed poorly. The B-29 system was already cutting edge, and airborne fire control radar was the absolute bleeding edge back in 1945. It simply wasn't quite there yet. The visual sighting stations weren't simply a matter of point and shoot. Gunners had to constantly frame incoming aircraft in a circle of dots to provide the computer with range information. A fire control radar could provide this information automatically. The radar dish was enclosed here above the turret. Later models contained two separate dishes. In fact, the radar on the B-36 basically carried out all of the complex tasks a gunner at a visual sighting station would typically perform. First, the radar typically operated in seek mode, where the dish would rotate and constantly scan the environment. Any targets would appear on screen at the gunner's station, and an alarm light would alert him to the presence of them. Secondly, the gunner could then manually track a target using a hand control to keep the radar pointed at it. Third, after doing so, the dish would then lock onto the target and continue tracking it automatically. The radar dish would maintain its orientation towards the target as long as it was in range. And finally, the range to and azimuth and elevation of the target were passed onto the targeting computer, which would point the tail turret in the appropriate direction. All the gunner had to do now was fire. We should remind ourselves, this was all carried out without digital circuitry. Here's the radar central unit. It had plenty of vacuum tubes, but these were for signal amplification and rectification. The radar tracking was achieved entirely with analog circuitry. One of the main reasons I purchased a copy of the gunnery manual was to try and figure out exactly what this process looked like to a tail gunner. I really wanted to know exactly what he saw when he was scanning and looking for targets. So here we are, in search mode. The screen denoted azimuth and range to target on the two principal axes. As the dish swept, the search window would be visible. Any potential targets would appear as fuzzy horizontal lines. A line would reach maximum brightness when the radar was pointed directly at it. Remember, the radar would also be scanning in elevation, but that isn't visually represented here. Though the elevation, azimuth, and range was still passed to the fire control computer automatically. In addition, the tail turret contained gyroscopes to pass the target lead data to the computer. As always, you can check out the relevant chapter on my B-29 video for details on how that worked. In tracking mode, when a target had been locked, the window would be narrow and remain locked onto the target. Though only analog circuitry was used, it isn't too difficult to imagine some kind of circuit that used feedback loops to continually seek and make the dot as bright as possible, where brightness is actually return signal strength. All of this is described on page 69 of the Fire Control Manual. Page 69 repeatedly makes very clear that those fuzzy target dots are called jizzles. Once a jizzle was being tracked, the gunner could hit his fire button and spray his freedom seeds all over it. As far as I understand, the radar tracking system worked well in tests. It proved able to accurately track targets to a range of 3,500 yards and hit them reliably at 1,000 yards. The turret itself was subject to all the issues the other turrets were, and we'll get there soon. But I do find it fascinating that reliable automatic target tracking was possible on such an old aircraft. That said, there were clear disadvantages. As the operator tracked a target, he was essentially blind to any other aircraft. So aircraft attacking in groups would essentially be invisible to the tail gunner if he was locked onto a single one, as the radar dish would track his selected target only. Furthermore, it would be difficult to determine whether a target was destroyed or breaking off an attack. It's conceivable that a gunner would continue pursuing an already destroyed aircraft instead of returning to seek mode and targeting other aircraft in an attacking group. Now, the system I've described is the APG-32 radar. In 1952, some of the aircraft were fitted with the improved APG-41, which theoretically solved these problems. The APG-41 consisted of two separate radar dishes. In some cases, they occupied two separate radomes. In other cases, they shared a common radome. Not only did this provide the operator with a second screen that also showed elevation on an axis, but it also allowed him to track with one radar whilst keeping the second radar in seek mode. A well-trained operator would be able to reprioritize and track targets as appropriate by monitoring both displays simultaneously. By 1952, the issues of the armament system as a whole had become widely visible and problematic. LeMay had personally complained about the issues to USAF headquarters in Washington, and the Defensive Armament Group had been set up to address the issue. However, the standout element was the APG-41 radar system, of which the group stated, quote, "If the APG-41 proves as satisfactory in simulated combat operations as it has in test operation, it is highly desirable that every effort be made to get the APG-41 installed in all B-36 type aircraft as soon as possible." End quote. See that little nose turret? It doesn't look too important in the grand scheme of things, does it? That turret is the main reason the B-36 looks so weird. Okay, I've avoided it long enough. The B-36 looks hideous. But take a look at the first prototype, the XB-36. That looks okay. It's funny how sticking a greenhouse on the top of your fuselage makes the whole aircraft look like an intercontinental thermonuclear sex toy. Studies of data from the B-29 raids led the USAAF to conclude that a dedicated nose turret was required in addition to the front dorsal turrets. They did also suggest the separate cockpit for the pilots and engineer, and proposed raising it above the main line of the fuselage. But to incorporate that turret into the high visibility forward section without impeding pilot visibility resulted in this. Now, that forward section was lacking in crew space. Unlike the B-29 bombardier position, there wasn't really room for a pedestal-mounted sight for a crew member to scan around with. The front gun sight is what I want to talk about in this chapter. I think it may have been unique amongst operational aircraft. The B-36 gunner didn't even have to move his head to aim. Here is the nose sight. It was connected to the turret via a computer, just as with the other sights, and it projected a reticle which the gunner framed incoming aircraft with, just like the other sights. But documentation on it is difficult to come by. In the end, I resorted to going through the patent from the Farrand Optical Company who designed it. The sight was a specialized telescope-periscope combination. That little protrusion on the forward window of B-36 houses the main elements of the periscope. Two prisms. The rear prism scanned in azimuth, and the front prism scanned in elevation. You can already see here how this would be useful. If both prisms are aligned with a target, the image of the target appears in the rear prism. We could imagine that image being cast onto a hemispherical surface, maybe made out of frosted glass, and we already have a rudimentary sight. Of course, the image will be reversed. A target at the front of the bomber will appear at the edge of the sight, and the image quality will be terrible and distorted. So instead of a frosted glass hemisphere, a series of lenses corrected those issues. I'd love to tell you how this arrangement works, but I know basically nothing about optics, and I couldn't get the whole assembly to model in Blender. I did try. I am a long way from that guy who built a working camera in Blender. But the arrangement is actually two telescopes, one pointed at each other. The aggregate effect was a clear picture of the region of the sky the prisms were pointed at. Another prism at the rear of the sight projected the sight reticle onto the image. The bicycle grip was used to adjust the reticle size. As with the other sighting stations, Celsin motors transmitted all the rotations to the computer. Though I couldn't get the whole setup to simulate properly, I did get this simpler version working. We can at least get an idea here of what the gunner would see, although he'd see it less distorted than my model. Going back to the front prisms, the front one actually rotated with the rear one. That was one of the unique innovations of this sight. Let's imagine if it didn't. The prisms would be independent and the rotations passed from them through the Celsins and to the computer would be in a different coordinate system to the turrets. The turrets rotate in elevation on top of a base which rotates in azimuth, just like the prisms in the sight as built. So the sight operated in the same coordinate system as the turrets, making sighting easier for the gunner and removing the need for a computer to mechanically convert from one coordinate system to another. Though the front sight was undeniably clever, it had issues. Mainly delays, with Kodak being contracted to make up the production shortfall after Farrand were unable to keep their schedule. The window was liable to frosting over, but this was fixed by a heater and a desiccator system. The sight was actually eventually the subject of a lawsuit, with Farrand eventually suing the US government for copyright infringement, but honestly, I'm not interested in lawsuits. Mechanically, though, the sight seems to have functioned well, so I think we can call it a success on that front. When I decided to make this video, I anticipated singing the praises of a lesser-known aspect of the B-36. The more I read up on the turret system, the more it became apparent I was going to have to include an entire chapter just on its deficiencies. The B-36 defensive armaments were never used in combat, so we'll never know for sure how effective they would have been. As it became apparent the B-36's primary combat role would be a strategic nuclear bomber, the doctrine of sending entire squadrons of bombers became obsolete. The peacemakers would act alone, their primary defensive measure being their altitude and speed. As the turrets were relegated to a secondary defensive measure, perhaps less focus was dedicated to their development, or maybe the simple reduction in manpower and resources precluded Corsair from properly integrating and testing a system that could improve upon that of the B-29. Either way, let's discuss the major issues encountered between 1949, when an incomplete turret system was first fired in flight, to 1954, when the decision was made to strip most of the turrets from the aircraft. We'll start with some basic stats. Gunnery trials involved flying the aircraft with a full load of ammunition to a designated altitude, typically 40,000 feet, which was the nominal cruising altitude. All turrets would be fired either to depletion or until a malfunction occurred. The total percentage of rounds successfully fired was the fire-out rate. The target fire-out rate from the Air Force was 90%. Considering all guns were fitted with charges to clear blockages, this doesn't sound too overly ambitious. In 1950, fire-out rates were typically 75%. By 1952, changes to address other shortcomings of the system had caused the fire-out rate to fall to just 60% across 14 missions. It's heavily implied in some records that lack of ground crew and maintenance contributed to the fall in fire-out rate. By July 1952, LeMay ordered armament and gunnery personnel to work 12 hours a day, 6 days a week, until fire-out rates of 85% were achieved. Because LeMay was, well, I don't really swear in these videos, do I? Anyway, the issues were never fully resolved. 76.5% fire-out rate seems to be the best attained performance for the overall system. Oh, and by the way, the turrets consistently most likely to fail were the tail and aft ventral ones, the most important turrets on the aircraft. Possibly the most comical issue with the system was with the thyratrons. As with the B-29, these were present to convert AC current from the generators to DC to drive the turret motors. The heavy guns needed powerful motors which demanded a high DC current to rotate at the desired speeds. Although it seems they never really did rotate at the desired speeds. Before solid-state electronics, this was achieved with a gas-filled tube. Alternate current supplied to the anode ignites the gas inside into a plasma, allowing current to flow to the cathode. As you can probably imagine, this had the tendency to create a lot of RF noise. From the Comprehensive History of America's Big Stick discussing early testing of the system in 1945, quote, radio frequency emissions from the fire control system electronic components interfered with the functioning of virtually every other item of electromagnetic radiating or receiving equipment aboard the bomber, including radars, radios, and electronic countermeasure equipment, end quote. Though shielding and presumably improved circuit design mitigated this issue, the Thyratrons were a source of ongoing grief as long as the turret system flew. Loss of power to turrets due to Thyratron failures were commonplace. During tests in 1953, 21 of 43 system failures were due to turret power failures. And in one instance, a rainstorm knocked the Thyratrons out. It's unclear whether it was because they got wet or whether it was due to lightning. Probably the next most common cause of turret failure was mechanical, either guns jamming or failing to feed properly. Convair themselves conducted 29 test flights in February of 1952 specifically to address these issues. 220 malfunctions occurred during these flights, of which 29 were failures to eject or extract ammunition. And then there was the ammunition itself. As you may have gathered, I don't really know anything about guns. I was surprised to read that the rounds were fired electrically. Instead of a firing pin, an electrical current was applied to the primer, igniting it and firing the round. I had to ask some folks in my Discord about this, and apparently it's the norm for tank ammo these days. But in the case of 20mm ammo on the B-36, it caused nothing but problems. As the jamming issues became apparent, the system as a whole was oiled liberally to try and mitigate the issue, but the oil would often form an insulating barrier to the electrical charge, causing failures to fire. The issue was later resolved by coating the rounds in wax and leaving the primer bare. More concerning, and therefore more hilarious, was the tendency for the guns to spontaneously fire uncommanded. And there were at least two mechanisms for this. The first was accumulated static charge, setting off those electrical primers. No word on how often this actually happened, assuming it did actually happen. But with 6 propellers turning, there was a lot of potential for static charge buildup on the B-36. The second, and probably far more common issue, was cook-off. This repeatedly occurred on record. During firing trials, guns would fire prolonged bursts and therefore heat up. Then a jam would occur, as we've already discussed. In the case of a jam, the turret was left extended. This is because those big bulky 20mm guns had enough thermal mass to heat up the trapped round and spontaneously fire it off. The huge frame of the B-36 required extensive contour followers on each turret to physically stop the guns from pointing at the aircraft itself. But those did not cover deployed landing gear, so there were concerns a stuck and overheated turret could cook off and destroy the main gear. To be completely fair, the cook-off issue was eventually partially resolved with the addition of a holdback release switch, which would close the chamber and prevent a round being chambered on a hot gun. Contour follower or not, after use, the forward guns were stored pointing directly at the forward crew cabin. Considering all the above, would you be comfortable sitting here? This one really does seem to lean more towards the what the hell were they thinking end of the decision spectrum. When the turrets did fire properly, they still caused problems. As I've now made clear, the system was clever in isolation, but its integration into the B-36 left a lot to be desired. The earlier iterations of the turrets looked like this. The guns were connected rigidly to the turret, which sat on its mount bolted firmly to the fuselage, so recoil from the guns was transmitted directly into the fuselage. Not only did that lead to unacceptable accuracy, but it had the tendency to shake apart the delicate onboard electricals, which, remember, largely consisted of vacuum tubes. This came to a head in November 1950 with possibly the most ridiculous aircraft crash report I've ever read. I don't have time to go over the whole thing here, but the crash of B-36 registration number 44-92079 could genuinely form the basis of an entire movie. It would be flat out hilarious if it didn't kill 2 of the crew members. Amongst many, many other issues, pretty much every element of the gunnery system failed, and more importantly, vibration from the guns disabled a whole host of electrical systems on the aircraft, including those controlling the fuel mixture to the engines. This ultimately led to a crash and gave the B-36 a place in the surprisingly populous club of aircraft that have shot themselves down one way or another. Is the B-36 the only aircraft with a kill ratio of -1 to 0? I think I need to do a dedicated video about that crash on Patreon. The second variant of the turret system added spring dampeners to the guns, which largely mitigated the vibration issues. So, let's assume we hit that once-in-a-blue-moon event. We get to cruising altitude. The guns deploy okay. They fire without jamming or randomly cooking off. The aircraft doesn't shake itself apart. Did we hit anything? Honestly, it's difficult to say. Gunnery trials did seem to indicate the guns were accurate against towed targets, but there were repeated complaints about guns not following sights properly. Additionally, vibration from the propellers would throw off the aim, particularly for the forward turrets in that cantilevered section. Even in this propaganda video, which was meant to showcase the B-36 to the public, the guns noticeably lag the sight. Compare that with the B-29 turret, and it's a world of difference. So, I think it's fair to say the B-36 turret system was cool. It was supposed to be a heavier and better iteration of the B-29, but the implementation was terrible. Had it been developed under the same pressure as that of the B-29, maybe the story would be different. In 1954, the decision was made to repeat learnings from the B-29. All but the tail turrets were stripped out, saving about £12,000. The increase in cruising altitude and airspeed was generally agreed to be a better defence than the B-36's janky turrets. Instead of putting the guns on the B-36, why not put them on another, faster aircraft? Of course, I'm referring to a fighter escort. But of course, fighters didn't, and still don't, have anything like the range of a B-36. So escorts were impossible. Or were they? The various Parasite fighters proposed, and in some cases actually flown on the B-36, feel like the aviation equivalent of a cult classic TV series. I'm going to keep this chapter quite brief because Not a Pound for Air to Ground recently put out an excellent video covering the history of these aircraft in great depth. I thoroughly recommend you go and watch that. Of course, when someone says Parasite fighter, most of us jump to this, the XF-85 Goblin. My intro has probably not helped with that bias. The reality is, the Goblin, though intended for the B-36, never actually flew on one. It conducted several test flights, but those were all from B-29s. It was 1948, and the brand new B-36 was simply not yet ready for this level of tomfoolery. That said, the XF-85 is often the butt of jokes because it looks pretty hilarious. But as Not a Pound for Air to Ground's video explains, it was honestly a really impressive feat for the time, and may not have been quite as ineffective as may seem at first glance. Back in 1948, there were no MiG-15s. For a brief window in time, the Goblin could have potentially run rings around the propeller-driven fighters the Soviets would have sent at the B-36. But of course, things moved on. The Goblins proved extremely difficult to handle on their test flights, all carried out by Edward Schoch, whose actions during those test flights can only be described as heroic. There were other Parasite configurations tested on the B-36, but the one I want to focus the rest of this chapter on is notable, because it was actually operational for a short period. FICON, or Fighter Conveyor, saw an RF-84K fighter carried in the bomb bay of a B-36. We'll get to the RB-36 later. It was the reconnaissance variant of the B-36. Of course, an RF-84 can't fit in a B-36 bomb bay, so it was carried more under than inside of the B-36. Deployment and retrieval were carried out by this large trapeze assembly. Crucially, the fighter pilot was able to exit his aircraft and board the B-36 via a catwalk inside the converted bomb bay, so he wasn't confined to his cockpit for the entirety of a long-duration mission. And this configuration actually flew missions, not just test flights. Albeit for less than a year, around 1955, RB-36s would depart Fairchild Air Force Base and rendezvous with an RF-84 from Moses Lake. The two would fly to the edge of their target zone, whereupon the RF-84 would be deployed via the trapeze and overfly the target at high speed to avoid interception. The reconnaissance equipment was fitted onto the fighter, with the B-36 loitering at the edge of the zone ready to meet up with the fighter again. In some cases, the RB-36, I believe, would also do high-altitude flights over the target region, so not necessarily just loiter and waiting for the fighter. In this sense, fighter may not be the best term, as these RF-84s were primarily for reconnaissance, but they did still carry 450 caliber guns. Or did they? I've been told that the display RF-84 at the National Museum of the US Air Force has the gun ports covered. It seems there may be some ambiguity here. Let's just go with the RF-84K carried between 0 and 6 50 caliber guns. There were proposals to extend this to a fighter bomber variant. The RF-84 would carry a Mark 7 nuclear bomb, or possibly a higher yield bomb depending on the mission. As with the reconnaissance variant, the B-36 would be relegated to a range-extending mothership, deploying the now fighter bomber near the target, allowing for a high-speed bombing run before returning for docking. I believe all the aircraft I've mentioned in this chapter are now housed in the Air Force Museum in Dayton, Ohio. People keep telling me I need to go there. I fully intend to sometime soon, but I couldn't get there ahead of this video, so awesome 3D renders it is instead. Either way, when thinking of wacky B-36 configurations, the Parasite fighters are probably the first to come to mind. And indeed, many of the tests were fraught with problems, peculiarities, and even crashes. But the reality is, the Parasite fighter that actually flew operationally with the B-36 appears to have been considerably more reliable and effective at its role than the turret system which forms the bulk of discussion for this video. Only the Americans would give the B-36 the nickname Peacemaker. The B-36 could carry a colossal quantity of peacemaking apparatus. General-purpose bombs, light-case bombs, armor-piercing, fragmentation, cluster, earthquake, radio-guided, incendiary bombs, depth charges, sea mines, and even photo flash bombs for reconnaissance. For those unaware, a photo flash bomb is basically a giant flash bulb, just to add a bit more to the Looney Tunes factor. Bombs could be split between 4 separate bays with a max load of 87,200 pounds. Again, for something built during the 1940s, that is frankly jaw-dropping. It's more than the max load of a B-52. On one occasion, 86,000 pounds of bombs were carried on a 3,100-mile flight and dropped halfway. That's about the same distance as the Marianas raids carried out by the B-29s on Japan in World War II. And the B-29s could manage a 15,000-pound bomb load over the same distance on a really good day. And don't forget, the B-29 was absolutely revolutionary for its time. Now consider the B-36 could carry 5 times the load over the same distance. Though I've been joking around a lot in this video, it's always good to remember nothing came remotely close to this thing at the time. Those numbers are still impressive today. But when you think of the B-36, you don't think of conventional bombing. You think of nukes. When the aircraft was under development, the team at Convair weren't even aware of the existence of Project Manhattan. But shortly after the war, B-36s were redesigned to carry and deploy nuclear weapons. That is a Fat Man-type nuclear bomb. You'd think, after one of those devastated Nagasaki, humanity would collectively take a step back and reconsider, well, everything. But of course, no, we went the other way. By 1954, the B-36 was required to carry this. That is a Mark 17 thermonuclear bomb. This is the largest bomb ever developed by the US. Anyway, here's Castle Bravo. Here's New York for scale. Jesus Christ. Suddenly, this doesn't feel like a silly video about the big plane anymore, does it? These fusion bombs weren't just city busters, these were bombs for burning countries. I'll do a really serious and somber talk about nuclear warfare and disarmament in another video soon, so I suppose we'll move on and keep the tone a bit lighter now. The Castle tests were monitored by airborne instrumentation carried on featherweight B-36s. These managed to sample atmosphere at altitudes up to 55,000 feet. That is well into Canberra territory. In fact, the Canberra was unable to carry the instrumentation to the required altitude for the Castle tests, which necessitated the use of a B-36J instead. You can add that to the impressive B-36 engineering feats list. Some of the aircraft used to monitor the Castle tests suffered severe blast damage from the detonations, particularly the one assigned to the big whoopsie moment that was Castle Bravo. This very much called into question the ability of the B-36 to survive its own bomb, but I don't know, honestly, once we're at the country-burning stage of a war, I'm not really sure how important that question is anymore. The Mark 17 is the start of another infamous incident, the Peacemaker that dropped a nuke on New Mexico in 1956. It wasn't quite as dramatic as you think. The bomb didn't have its plutonium core in place, but on approach to Kirtland Air Force Base near Albuquerque, a crew member may have accidentally triggered the bomb release. Mechanical failure may have played a part, and the crew member was exonerated of any fault afterwards. Now, the bomb fell straight through the closed bomb bay doors, the aircraft lurched several hundred feet upwards, and a gunner called "bombs away" over the intercom, which I think is hilarious. On contact with the ground, the explosives detonated, scattering uranium all over a field and creating what I can only imagine was a bit of a decontamination headache. It's often claimed a cow was killed by the blast, though that does feel a bit like an embellishment to the story. But the bomber itself was landed with no harm to the crew. Ten engines meant a pretty comprehensive instrument panel for the flight engineer. You may have seen photos of it before. The four jet engines were a later addition that allowed the B-36 to get off the runway with a heavier bomb load and also significantly increased the cruising speed in the combat zone. But I want to focus on the six incredible Wasp Major radial engines that drove those propellers. These were, and still are, the pinnacle of aircraft radial engines. Now, being British, I'm normally more of an inline liquid-cooled type of guy, but I appreciate beauty when I see it, and I went to see one of these things in person. There's one sectioned and motorised for demonstration at the Isle of Man Motor Museum. In fact, they have two. The other one is in its original transport container. Now, as our friends across the Atlantic like to say, there's no replacement for displacement. Except there is a replacement for displacement. There are plenty. Forced induction, direct injection, water methanol injection, to name a few. The Wasp Major displaced 4,362 cubic inches. Alright, sorry, I need to do non-freedom units for that. That's 71.5 litres. Barring some Soviet vanity projects, it's the most powerful piston aircraft engine ever mass-produced. And those replacements for displacement, it used all of those too. There were multiple variants, ranging from the initial model with its single-speed, single-stage supercharger resulting in an output of around 3,000 horsepower, all the way up to the 53 variant, which saw the addition of two parallel turbochargers for use in the B-36J variant. There is some ambiguity in my sources on this, but the B-36J flight handbook states there are two parallel turbochargers. The excellent book Pratt & Whitney's Wasp Major Miracle by Graham White seems to suggest this variant still had the supercharger in place. So I assume the parallel turbochargers fed into a single supercharger. This gave a total of 3,800 horsepower. By the way, in that book, White gets visibly annoyed that people refer to the engine as the corn cob. I mean, I'm totally with him. The Wasp Major was a miracle of engineering, and that is not a suitable nickname in my opinion. Regardless of the exact arrangement, forced induction was essential to allow the engine to operate at high altitudes. I cannot go into the technicalities of exactly how various super and turbocharger arrangements best lend themselves to performance at various altitudes, but if you want literally hours of that, Greg's Airplanes and Automobiles is the channel to go and visit. He also has an entire video on the variable discharge turbine, which is a natural progression of all the above, and one of several things that almost but never actually flew on a B-36. This later variant of the Wasp Major had direct fuel injection too. Not only did this increase available power further, but it put an end to the notorious engine fire issues with the B-36. Now, taking a cursory glance over some crash data, it doesn't seem the B-36 was actually any less reliable than other large aircraft of the time. If anything, it actually seems to have been involved in less in-flight incidents than was typical. But a repeated issue was carburetors icing up. This was not a fault with the engines themselves, it's because they were mounted on backwards. The cold incoming air would flow into the carburetor, which was situated forward of the engine. The Venturi flow inside the carburetor would cause icing, limiting airflow, giving a fuel-rich mixture which could then ignite in the exhaust. The magnesium wing panels were then liable to igniting, bringing down the aircraft in a matter of seconds. Throughout this video, I've pitched the B-36 against MiG-15s. After around 1954, the Soviets began fielding higher performance jets, such as the MiG-17 and 19. Those essentially rendered everything I'm about to say obsolete, and are the reason for the B-36's short service life. A B-36 typically cruised around 40,000 feet and 200 knots, 378 knots with the jet engines active. A MiG-15 service ceiling was around 50,000 feet, and it could manage somewhere around 450 knots at the B-36's altitude. I always had these comical images in my head of B-36s appearing over the Soviet Union with this video's intro in mind, only to be instantly swarmed by MiGs and shot to pieces. This would be unlikely. Being able to get to altitude is only the beginning. As altitude increases, air temperature and therefore the speed of sound decreases. A MiG-15 could not fly supersonic. Supersonic airflow over the wings would destabilize it and cause the pilot to lose control. However, the lower air density at altitude requires higher airspeed to execute a steep bank. Not enough airspeed means not enough airflow over the wings, leading to a stall. You may have heard of this region in the flight envelope, where the margin between stall speed and Mach limit is limited, as coffin corner. In practice, this limited MiG-15s at the B-36's cruising altitude to shallow and slow turns. The B-36, on the other hand, with its huge aspect ratio, could easily turn inside of F-86, F-89 and F-94s in trials. By extension, they would easily be able to force MiGs into a tail chase. That would allow the lethal and effective tail turret to come to bear against a pursuer struggling to maintain control near his service ceiling. And that assumes the MiG even had the fuel left after the climb and pursuit. Unless swarmed by many MiGs from multiple directions in a highly difficult and coordinated attack, it was widely believed a MiG-15 could not intercept a B-36. Some of the J variants I mentioned earlier became the RB-36, the reconnaissance variant, and the one with the highest service ceiling. These contained a suite of electronic countermeasures long enough to make an entire credits scroll screen from. These were housed in the converted bomb bays, which also contained a darkroom for developing captured photos, in the field so to speak. For those who watched my last video about the crewed Almaz spy satellites, it's fair to say the RB-36 was a kind of proto-Almaz. And just like Almaz, the RB-36 started life with all the guns I mentioned earlier, but they were eventually removed to increase the service ceiling. The introduction of the F-100 in late 1954 seems to have given Strategic Air Command a reality check, however. That could easily outmaneuver a B-36 at altitude, and over the next few years, the Peacemaker was taken out of frontline service. I like to end my videos with a chapter on something related to the main topic but not quite central to it. This chapter is about an aircraft which could have eventually taken the defense by superior propulsion concept to its limit. NB-36. The N stands for nuclear. And after some further reading, it turns out the N did not stand for nuclear. It stood for this, somehow. Moving on. And guys, it looked really good. Seriously, half the reason I chose the NB-36 out of all the modified Peacemakers was because it was a looker. Turns out dropping the greenhouse and giving the B-36 a nose job turns it into an absolute babe. And that paint job? Straight to the end of Alex's aircraft cool wall. I think it's a testament to the human spirit that it took us a mere 4 years from building the first nuclear reactor to asking, okay, how do we use one of these to power a plane? Now, I don't want to disappoint, but the NB-36 was not nuclear powered. We still haven't built a nuclear powered aircraft. Upsetting as that may be, we'll figure out why as I go through this chapter. The NB-36, rather, was the first practical step in building a nuclear-powered aircraft. It flew 47 times with a working nuclear reactor on board, but that reactor didn't actually power anything. So, the NB-36 in my intro made absolutely zero sense. I just thought the idea of one YOLOing straight through a formation and dropping a nuke was really funny. So, here's the idea. The B-36 had pretty good endurance. About 40 hours. But how about unlimited endurance? And no need to refuel, ever. But how do you power an aircraft with a nuclear reactor? The proposal was alarmingly simple. A jet engine burns fuel to produce hot gas, which is exhausted to provide thrust. Instead of burning fuel, just direct incoming air around the nuclear reactor and use the heated air to provide thrust. Feel free to list the potential issues with this in the comments. But on paper, it would absolutely work. The first step was to determine whether an aircraft could even fly with a critical nuclear reactor on board. So here it is, the P-1 airborne test reactor. It output a comparatively small 1 megawatt and weighed 20 tons. Metric. Yeah, I am not converting watts to whatever the hell you guys use over there to express power. Actually, I will. Why not? Okay, imagine if we took all the thermal energy output by that reactor and used it to drive a turbine with zero energy loss. Of course that's impossible, but just run with me here. 1 megawatt is about 1,340 horsepower, so you'd need about 3 of these just to output the same propulsive power as just one of those WASP major radials. I'm not sure whether that is a commentary on how small the reactor was or how powerful those piston engines were. The airborne test reactor used 3 control rods to limit output and would be managed by a dedicated nuclear engineer whilst in flight. These air scoops were added to provide cooling air, and the hot air was just dumped overboard. Again, the aircraft was not nuclear propelled. Now, I don't think I need to tell you how sketchy the thought of flying a nuclear reactor on an aircraft is. Even though it was 1955, the USAF were more than aware of this, and honestly, I have to applaud the precautions they took. First, the cockpit. It was specially built and lowered into the aircraft like this. It was lead and rubber shielded, with the windows being leaded glass and plexiglass up to about 10 inches in thickness. Hold up, 10 inches? Those are deep submergence vessel numbers. The entrance hatch weighed about 500 pounds and would fall open in the case of an emergency. In addition to the cockpit, the crew was shielded by an 800-pound lead disc in the fuselage. And of course, the distance between the reactor and the cockpit owing to the long fuselage provided protection in itself. On the ground, the reactor will be removed from the aircraft via a specially built heavily shielded crane and stored in a special underground compartment. To install it in the aircraft, it was suspended in the bomb bay via a single hook. In the case of an emergency, the reactor could be jettisoned at any time by opening that hook. The prospect of this is simultaneously hilarious and horrifying. Since crew could no longer sit in the rear section and watch the engines for issues, CCTV cameras were installed in the rear gunner windows and connected to displays in the cockpit. Now that feels extremely advanced for 1955. 46 of the 47 flights of the NB-36 were carried out over the New Mexico desert and 1 over the Gulf of Mexico. Each flight was accompanied by a B-50 specially modified with radiation monitoring equipment for testing purposes. Apparently, the crew of the B-50 were able to station keep from the MB-36 just by watching their radiation monitors. Again, horrifying and hilarious. In addition to that B-50, a transport aircraft with paratroopers would accompany the MB-36. In the event the reactor had to be jettisoned, or indeed the aircraft crashed, they would bail out and secure the area. Apparently some of them were paramedics too. Now, as a proponent for nuclear power, I think nuclear-powered aircraft may be my line in the sand. You may be thinking, just make sure the reactor's well shielded so it can survive a crash. And if you are thinking that, you may be picturing something like this. Well, that vessel, designed to carry nuclear waste, weighed about as much as the airborne test reactor, and that train was travelling at around 100 miles an hour. Now imagine a jettisoned reactor falling onto solid rock at supersonic speed. What we have here is a bunker buster, full of uranium. No amount of shielding that can be carried on an aircraft is going to keep that uranium inside. With all that said, and it is very easy to laugh at the sheer 1950s energy of flying a nuclear reactor around, I do think the USAF conducted the tests with appropriate safety measures. All the above ensured the crew were safe, and it seems they had plenty of contingency measures to deal with incidents. And, well, this channel is all about giving things a try, as long as you can do it safely. The findings from the HTRE test reactors that were built as part of the program went on to contribute heavily to the development of the molten salt reactor concept. Of course, the world then basically botched nuclear power for 50 years, but the concept's still there. If we ever do build commercial molten salt reactors, and for the record, I think we should try, we have the B-36 to thank for a small part of it. And if nothing else, we got a really cool looking plane to talk about. The fact that we're all alive to watch this video is a reminder that the B-36, of course, never served its primary purpose as a strategic nuclear bomber. In that sense, it was certainly ahead of its time. Very few aircraft even today can match its range and carrying capability. Most of the turret system was clearly obsolete as soon as it first flew, and that isn't even taking into account the design and implementation issues it faced. But the aircraft itself went down as a stepping stone between the piston-engine bombers of World War II and the jet age. The bombers were replaced by the B-52s, and the reconnaissance variant was replaced by the U-2. Both are still in active service today. As for armament, the 1950s moved the world into the age of the fast jet and guided missiles. Lots of big guns on multi-engine aircraft were very clearly a thing of the past. For about a decade.